Good morning, everyone.
So, shall I present you? Probably
Well,
you don't need to be introduced.
Well, my name is there.
Janssen, and he will talk about the method.
Sorry.
Yeah. Sorry about that.
No.
So, on the method to predict extreme wave events,
Yep.
please.
Okay, thank you. So I'm going to talk a little bit about extreme waves. Normally, I would call them freak waves, but people don't like that name usually, and they are referring to rogue waves. But I can tell you, rogue waves is not a good name either, because rogue is just connected to crooks, all kinds of negative things. And freak waves are, of course, a very beautiful thing to observe and to try to understand. Yeah? So I want to keep it positive in this way. Right, so this is an example of a freak wave event. This oil rig is on average 23 meters above mean sea level. And as you can see, now the wave is hitting the lower deck. And so it turns out that the crest height is something like 23 meters, which is quite unusual because you should realize there's also something below the sea surface. So we're looking at something like a 30-meter event or so, 35. And so this is a quite unique picture, because most of the time, we have no real evidence of freak waves at all, because it's really a very fickle event. It just happens very quickly. Say it lasts about 10, 20 wave periods, and that's it. Now, typical wave period for ocean waves is something like 10, 15 seconds. So that's a very short time that things happen. So, and the challenge is still to try to be able to say something about the occurrence of those events. And since, even for ocean waves, long-time integrations become very uncertain because of the sensitive dependence of the phase of the waves on the small changes in initial conditions. So we have to resort to statistical techniques to try to give meaningful information on those extreme events. Okay, so this was bad weather. Those things can also occur in fair weather. And as you can see, this is a very nice shape. You can create it also in the laboratory, so we know it's not fake, it's real. And so this is just caused probably by the interaction of the waves with the bottom profile, which causes the formation of an extreme wave. Okay, so I will talk today a little bit about predicting extreme waves, and call them freak waves. And I will give the main reasons why such extreme waves occur, and then I will describe a statistical method to predict these extreme events. So basically, basically the freak waves are caused by constructive interference of free waves giving steeper waves. And with a free wave, I mean a wave obeying the dispersion relation, in this case of surface gravity waves. Yeah? And so that happens occasionally, that you have a constructive interference, but of course probability that occurs is fairly small, but it can happen. But when it happens, you get steeper waves, and then you get a number of nonlinear processes which may give rise to focusing of wave energy. And one of those processes is the Benjamin-Fair instability. And then you get focusing because waves temporarily borrow energy from their neighbors. I will explain that a little bit more in a second. But this process is only pronounced for narrow band wave trains. That means when you have a narrow wave spectrum, narrow band wave spectrum. But when they occur, they may give rise to large deviations from normality. And for us, normality, which is described by the Gaussian distribution of the surface elevation, is the norm. And we are looking now to small deviations from normality, and then you can just apply all the things we've learned in statistical mechanics to try to describe things. Now, another process which may give rise to freak waves is wave-current interactions. They may increase steepness and therefore enhance the Benjamin-Fair instability. And then we also have bound waves. Bound waves are really connected to the free waves. And for instance, an example of a bound wave is the second harmonic, a third harmonic, etc. Those harmonics, they do not propagate with the dispersion relation. They obey a different relation for the phase speed. Now, as I pointed out already, at C only the statistical description of the phenomena is possible. And so, because freak waves basically are similar to the Luckhoff draw in the lottery. Now, from a knowledge of the wave spectrum, one can determine all relevant statistical parameters such as skewness and kurtosis of the C state. And from this one may evaluate the PDF of the envelope wave height and maximum wave height. And in particular, I will concentrate a little bit on shallow water effects. Now, let's now first discuss the main mechanism. So it's the Benjamin-Fair instability, which is basically an example of a four-wave interaction. So the linear dispersion relation for water waves is given over here. Omega is angular frequency, K is wave number, D is depth, G is acceleration of gravity. And this dispersion relation allows a resonant four-wave interaction, which is determined by the conditions given over here. Yeah, so for those four waves, you can have a resonant interaction, and then basically you get an instability. And it can be shown, and if I am quick enough, I can show that immediately, by means of a graphical construction, you can show that resonant three-wave interactions do not occur at all. And that's very easy to see if I'm allowed to move this. Maybe it's better here. So suppose, let's try to construct the case of a three-wave interaction for surface gravity wave. Now you should realize that the dispersion relation, let's just concentrate on deep water, is given by this square root relation. So this is the dispersion relation. And now let's try to construct, say, an interaction of this type. Yes, so this is the most basic three-wave interaction. And you can easily do that. I mean, this is wave number one. This is wave number two. And then the sun always ends up outside of the dispersion relation. It's not hitting the dispersion relation. That's because of that shape of the dispersion relation. And the only way to get something in resonance is to add another wave, a fourth wave, because then you can move this point to here. Okay? And that's basically it. So we only have four wave interactions. And well, the mechanism, the actual mechanism is described here. So suppose this is wave number, this is the spectrum, and suppose you have a carrier wave with a delta function peak given over here, and you perturb that by two sidebands, plus or minus delta K naught. Then if you would draw the actual situation, you would get a wave that looks like this. And the dashed line is the envelope, and that's what I will talk about very frequently in the remainder of my talk. And so this is basically a wave group. It's described in the narrow band approximation by what we call an envelope soliton. But anyway, so if the sidebands are small, of course, it will be almost uniform, the envelope. And then you will get higher sidebands, and then you get a stronger modulation. And then you see what happens. If your ship is sailing over here, and it moves into this area, then here sea state is very quiet, and all of a sudden it's very steep. And that is the phenomena of a freak wave. You know, then things get so steep that the ship can't cope with the forces exerted on it, and it will capsize or even go down. And so the mechanism is as follows. There's a resonant interaction, basically a resonant transfer of the energy of the carrier wave via the second harmonic to the sidebands. And the four-wave interaction is given over here. So K naught plus delta K naught. That's this one. This is the wave number of the other one. And then on the right-hand side, you have, say, either the second harmonic or twice the wave. And that gives you then a resonant interaction. Yeah, and that's a process that transfers energy from the carrier wave to the sidebands and giving then a very deep modulation. Now, in the course of time, if you just restrict to the single wave case, as I described before, including the two sidebands, what happens is if this is the amplitude of the sideband, then you get a periodic modulation like this, and the carrier wave amplitude is going like this. So it's just based on conservation of wave energy, you get this strong interaction. But here, of course, when the modulation amplitude is very large, you get a very deep modulation, and therefore a very strong freak wave. Okay, that's a simple case of a single wave. Of course, if you have a continuum of waves as we have in nature, things are completely different because you don't get this very nice periodic behavior anymore. It is just getting very confused, and you have to, in the end, you realize you have to look at probabilities. So there's a theoretical development, and it started basically by Gabor, and also Logan Higgins and Schrokers and Typhoon. And this is based on the statistics of the envelope of a time series of the surface elevation. And this, the definition of the envelope is basically given here. So the surface elevation, eta, is a very general process, no restrictions. It's just an envelope rho times the cosine of theta. So this is how you represent your process. And rho and theta are very complicated things. Yes, just not a single wave, it's just everything what is in that time series. Now, and what you then do is, you can also then introduce the Hilbert transform of eta, and that's rho times the sine of theta. Now, then you can write down the joint probability distribution function of eta and the Hilbert transform. And if you do a bit of work, then you can look at the characteristic function of the joint PDF, and then you can show that the normalized envelope wave height, which is defined here, it's 2 times the envelope divided by the significant wave height. It's just a typical wave height of the system. Then you get this kind of PDF of the normalized wave height. So the first term is a Rayleigh distribution, and then you get corrections due to kurtosis and skewness. Yeah, and the task is to try to figure out how those parameters, kurtosis and skewness, depend on the sea state. Yeah, you have to figure it out. And I've done that, say, 20 years ago, and that's just based on statistical mechanics of random ocean waves. Yeah, that's just the theory that started by Klaus Hasselmann in 1962. And I've just used that theory to calculate the additional information I need on the statistics of ocean waves. Yeah. Okay, so that's... now, the expressions you get for skewness and kurtosis are quite involved. And now you need something like a neural network, because, for instance, the kurtosis is a 6-dimensional integral over wave number space. It's 6-dimensional because this is a delta function in wave number space, so it kills off the wave number K4 integration. but it's 6-dimensional, and you should realize that typical number of degrees of freedom for a wave spectrum is something like, say, 10 to the third, 1,000. And so it's 10 to the third times, that's 10, it's an integration over 10 to the 9. So it's quite an involved integration, and you can't do that operationally. You can forget about it. So my task was to try to figure out, to come with approximations of this integral. And I will tell you a little bit later how I did that. But this of course, is interesting that it is such a complicated expression. But of course, now you might say use neural network approximations to try to get a better go at this kind of problem. And it's not a trivial integral here. The thing is this, that this resonance function is, it depends on time. Delta omega is the, if delta omega vanishes, then we have a resonant wave-wave interaction. And it also involves this denominator. So it's a bit of tricky integral to deal with. Okay, and then over here, N1, etc., is the action density. That's basically something like the wave number spectrum divided by the phase speed of the wave. Okay. Now, so this is a relation that exists for the kurtosis of the free waves, but you also can do similar calculations for skewness. Yeah, so in principle, everything is known in that respect. Now, what I've done is to get some confidence in the value of this approach. I did a Monte Carlo simulation for surface gravity waves, and I just assumed that I have an elevation which is given by this simple sequence. It's just a Stokes wave expansion. So this is a carrier wave, this is second harmonic, this is third harmonic. And to make sure, because you know, I have to go to very high values of dimensionless wave height, and so the probabilities that those things occur are very low. I did a 50 million member ensemble by drawing the amplitude A from the Rayleigh distribution, and the phase is from a uniform distribution. So it's a random phase approximation. And then you can do the work. And this is then the PDF of wave height as function of that dimensionless wave height. And the Monte Carlo results are given by the dashed line. And we go up to a level of 10⁻⁷. So that's it's quite small. Then if you would assume linear theory, just a Gaussian or a Rayleigh distribution, then you would end up with this PDF. Then the linear theory, as I described it just now, gives you this approximation. And of course, well, you get closer to the actual distribution. But as you can see, for large elevations, even that theory fails, because this is clearly different. This is an exponential distribution. And so I don't have the time for this, but I have added to this problem a patch to get an exponential distribution, and the result of that is given by this line. So, you know, for the really large deviations, you need to have an exponential distribution. Now, now is the task just to get some parameterization for the skewness and kurtosis. And so for given C state, you want to have this statistical information on envelope skewness and kurtosis. Now, I will treat the contributions of the bound waves and the free waves separately, and I will validate the parameterizations against exact computations using simulated spectra for two special cases, namely the Draupner wave. That was a big freak wave event on the 1st of January 1995. It was actually the first one where we actually observed things like a time series. And another big storm is the so-called Andreas storm. So basically what we did, we used our atmospheric system at the European Center, which is coupled to an ocean wave model called ECMWF. And IFS is Integrated Forecasting System of the European Center. So we use this coupled system to generate spectra for those events, for the Draupner case and the Andrea case. And that I regarded as the truth spectra. And then I use those spectra to generate kurtosis and skewness and try to make a parameterization of it. So these are examples of spectra. Don't look at the details. This is just basically the frequency. This is the direction. You know, of course, we have also direction as parameter because waves can propagate in different directions. And this is for the Draupner case. This is for the Andrea case. And, you know, we had also quite some variation, especially in this case, because this is initially what the spectrum was. So it was very broad, whereas these are much more narrow. And then corresponding time series for the Draupner case is given over here. So this is surface elevation in black, and the envelope is in red, and this is time in seconds. And at a certain occasion, we got a really quite big freak wave event. And the task is, you know, how likely is, according to our knowledge, this freak wave event? That's an interesting question to ask, and I will do that in a second. So then from the information on the spectra, we generated the parameters, time series for skewness and kurtosis. This is for the Draupner case. This is for the Andrea case. Again, skewness and kurtosis. And you can also look at time series of the event, but let's skip it. The only thing that is remarkable here is that for the Draupner case, the thing is fairly uniform. We always got the same type of evolution for every case of the spectra we considered, whereas for Andrea there was quite clear different behavior in times of the record. Now, so of course we want to know how likely this such an event is according to our knowledge. And so I'm introducing here the exceedance probability. That's the probability that maximum envelope wave height is larger than the critical value. And I assume that the PDF of envelope wave height is known, and I define the cumulative distribution function as follows. So that's the integral from the critical value to infinity. That's the cumulative distribution function. And then you can show, I won't give you any details at all, but you can show that the probability that the maximum envelope height is larger than the critical value is given by, in good approximation, 1 minus the exponential of minus n times that probability, this one, where n is essentially the number of events over a time domain of interest and a spatial domain of interest. And n is essentially the number of wave groups in your time series. Yeah. And so, following the work of a long time ago of Adler, we estimate that number n, and we take as a size of the domain the resolution of the wave model, which in our case in those days was 14 by 14 kilometers, because that's the minimum thing we can look at. And so then I can show you then next what the exceedance probabilities are. So that's the blue line. This is for Draupner, this is for Andrea. This is time again. And you see that we get something like an exceedance probability of in the order of 8%. And also for Andrea, something like 6%. And I've also shown, but I don't have time to discuss all the details, but I also showed the effects of when you ignore things. So for instance, when you ignore the kurtosis, then you will get this. So there's something like a factor of 2 to 3 difference in actual estimation of the probability. So that means that that process is quite relevant to try to estimate the probabilities. Linear theory is given over here, so actually nothing happens according to linear theory at all. Yeah, so and this is now the thing I would like to be able to predict with a parameterization. Now, so how did I do that parameterization? By the way, how much time do I still have? Because I don't know when I started. Yeah, okay, I'll make it then. So first the bound waves, that means the second and third harmonics, etc. And also the effect of waves on the mean surface elevation. That's also an important parameter to deal with. And so basically what I did, I was able to calculate theoretically the kurtosis and skewness of a single wave. You get an expression, and I can tell you what the expression is. Instead of this number, it's 2, and 0.9, it's 1, okay? And here, this is 8. And those parameters, alpha, beta, and delta, are basically parameters connected to the Stokes wave train. Yeah, so you can write down your Stokes wave solution, and you do that in shallow water. Then things get a little bit more complicated than in deep water because you get an additional dependence on depth, of course. But anyway, you can all do that. And then you get this expression, and I just modified the expression by also modifying things like how you define the steepness. Epsilon here, so normally it's k times a is amplitude, but I modified that definition in such a way that it applies more to a spectrum of waves, etc., etc. So that's what I do. And then I validated that against the exact calculations, and the result is this. This is for skewness, this is modeled, skewed, parameterized, and this is exact. And here for kurtosis of the bound waves. And you can see, you know, for those cases I can do a reasonable job. But of course, you guys in artificial intelligence can do a much better job, I suppose. But you know, that's how far I could go on this subject a few years ago. Then the free waves is a bit more of a challenge. Then you should realize that I was talking about this four-wave interaction process, and there are special circumstances under which this process is very efficient. And that is when you have a very narrow band spectrum in frequency, and you have a very narrow band in direction. In those cases, you get very efficient transfer of energy from the carrier wave to the sidebands, and therefore a rapid broadening of the spectrum. And this is then associated with a rapid increase in kurtosis, as we will see in a moment. Now, the two parameters in question are called the Benjamin Fair index. That's basically the ratio of the steepness of the wave squared divided by the width in frequency space. And then you also have a directional parameter which measures the importance of the direction. That's the ratio of the width in direction over the width in frequency. So to get it really efficient, you need to have that delta theta is less than delta omega, and the BFI should be of the order of 1. Those things occur, but they are quite rare, but we know that they occur. We have validated all those ideas, by the way, in the laboratory where you can do things at your ease. In nature, it's of course much more difficult because, as I told you, the phenomena does not last a very long time, so you have a very low probability of meeting it actually. Okay, so now then, in the narrow band approximation, you can approximate that six-dimensional integral, and then it looks like this. So the kurtosis of the free waves is something like the Benjamin Fair index square, and this parameter gamma j is this integral over spectra and involving that resonance function again. So now for a very simple spectra, and by the way, the frequency, what is it, the mismatch in frequency is defined over here, and it involves the parameter R. So now for a very simple spectra, it's basically Gaussian shape, you can solve this problem exactly. Yeah, you could just get an exact expression, which is not too bad. Also for finite R. Initially I found an exact solution for R equals 0, but later Fedele helped me out to find it in the two-dimensional case. And let me see. So this is then, you just then need to know how this factor J depends on time, and that's given over here. So this is J normalized with something, a factor given over here, not relevant now. This is time, dimensionless time. And you see when you have no directional distribution, then it goes towards a steady state. But for finite width, you get a transient phenomena. So initially you get a big value, and then it decays to 0. And I can prove that it really decays to 0 for this case. Yeah, so the thing that I can do then is just to estimate the severity of the C state by looking at the maximum value of that norm. And I've given here two expressions. This one is the one we used. This is, by the way, my brother who helped me out in doing all the analysis, because it's not so trivial. You know. Okay, so and this is then the validation of the approximation used for the maximum value of kurtosis. So the full line is given here, and I'm colorblind, you know. So the thing my brother and I found is given by this color. So I think it really matches the numerical results very well. Okay, so, and that's what we use then in our prediction system. And then you get as validation here, this is the kurtosis for the free waves against the exact one. And this is then the total kurtosis as function of the exact one, because also the bound waves have contribute to kurtosis. So you get still a fairly good approximation, you know, it's something like, I don't care about correlations, but something like 98% is not too bad. If you realize that initially I had correlations of 20%, then that tells you it's a bit of a sensitive thing, and etc. And so here, then I show here the comparison between the exact calculation and my parameterization for the exceedance probability. And as you can see, that matches pretty well. There's hardly any difference. This I skip. Very interesting, but that, yeah, so we, of course, we always validate things on a large scale. So my colleague, Jean Bilot, and I have implemented these changes in our operational system. And to just get an idea, this is, again, skewness, this is kurtosis, as function of a parameter which characterizes the stage of development of the C state, and we call that the wave age. The wave age is basically the ratio of the phase speed of the peak of the spectrum normalized with the friction velocity. So if Cp is much larger than the friction velocity, then then the wind has no effect on the waves because the waves are too fast. Okay, so only for small values here we are, in this case, around 1. We are looking at the wind waves, and here we are looking at swell. And that's also for the same for here. And so this is the kind of thing you can produce. And we of course try to validate it and have validated the system against the observations of what we call maximum wave height. You know, that these are available from the buoys, because you just get your time series from the buoys, and then you do your envelope, and then you estimate the maximum envelope of that period, and then you just compare. Yeah. Okay, and this is then the PDF of the globe of maximum wave height. So this is maximum wave height. Things get critical in practice if we have a maximum wave height ratio of about 2.5. And this line is linear theory. This is the complete theory, and this shows you that, you know, also for the maximum wave height for large values we have an exponential distribution. Okay, so that's it then basically. So I've made an efficient parameterization of skewness and kurtosis, but of course it's based on a fairly small set of cases. It works for those cases for Draupner and Rea. And, but of course it might be interesting to see how we can generalize this to much more different cases. Thank you.
Thank you very much. Question? Okay.
Thank you, very nice presentation. In the ocean, how many of these freak waves do we typically observe per year? I mean, clearly you showed that nice example that was hitting an oil rig.
Yeah.
So occasionally we hear some ships being hit by them. So how many of them do we actually see, really?
Actually see, well, I don't think we actually see many, but we, of course, we realize that when a ship goes down or so, then something might have happened, and then we try to simulate it. Of course, we can look at the statistics of our system, how often it happens, but I've forgotten that number now. I'm retired 5 years ago, you know. So, but I think you still get a decent number of several hundreds per year, you know, of really serious cases.
Would current satellites be able to see those waves? Is that
well, that depends.
Too short a phenomenon for that?
Yeah. No, certain satellites are able, like an altimeter, they are able to detect those extreme events, but you have to do special processing for that. And the hope was that also the synthetic aperture radar could do that, but that filters out lots of phenomena, so that makes it difficult. But in principle, you could hope that satellites will give information on that. Yeah. There was someone in the back. Oh,
okay. I'll be moving like this.
Peter, you started by saying that the predicting these things was no different to predicting the lottery, but in a sense you are describing a statistical prediction system which presumably has more predictability than the lottery, which has no predictability.
yeah.
Or maybe I misunderstood. My question really is, I mean, from all this work you've done, can you distill any kind of rules of thumb that you could give to sailors or mariners more generally?
Yeah.
So, but what comes out of it that are key, the key predictors?
You have to avoid narrow spectra. You have to avoid frontal systems. If they are very vigorous, then the wave system is pushed out of equilibrium. And when you push it out of equilibrium, then you get this change of the kurtosis. So we can tell them immediately. And we have examples. I don't have it with me, but we have examples archived where you could see. You know, there was, for instance, the cruiser Dawn in 2008 or 6 or so, and they had an incident. And then we looked at this case. It was just a frontal system, rapidly changing wind, that forced the waves out of equilibrium, and you know, so those things we can just guide.
I guess there are no rules of thumb for lottery, winning the lottery of a similar type.
Well, yeah, I have. As you know, I've used your EPS system to to predict whether Wimbledon was dry for 2 weeks. So, and I won. So
But not the national lottery. I don't think you can use the ensemble to predict the national
yeah.
lottery. Anyway, sorry. Okay.
No, but you can use ensembles to help you out a little bit. Yeah.
Thank you. Pierre, did you have a question? Okay.
Okay, thank you. I mean, really interesting talk. I was looking at so you're adding your non-linearity and you have your exponential tail, so it's heavier tailed.
Yeah.
Have you tried looking at it with an extreme value distribution and looking at the shape parameter, which is another way to capture ketosis and skewness?
Yeah. People have done that. I haven't done that, but you know, it's of course very similar to what has been done before. But the only thing is I've used this exponential distribution. It's also observed in other fields, like maybe that he is pointing it out. But you know, that exponential distribution is really a very powerful way of characterizing the extreme C state. Because you only need one parameter it's just amazing.
Thank you.
I have more comment than a question. In all your very important works, you always are based on a statistical approach. And behind the word Benjamin Fear instability, people from the nonlinear dynamics community will think about the dynamical mechanism much more than the statistics, okay? And it's known since 2015 by the work of Zakharov and Agafonsev that if you start just from a plane wave in the focusing nonlinear Schrödinger equation, the long-term evolution of the statistics goes toward the normal law. So, which means that in the random wave process, the mechanism is different, and one of the main assumptions is that it's related, to what is called the gradient catastrophe. So, it's just a comment about the fact that, of course, even the gradient catastrophe is related to the narrow band instability. Okay, of course. But I'm just comment on the fact that the word Benjamin Fear instability in all your work might be confusing for people from nonlinear dynamics, okay, because...
Oh, well, they have to listen better then. Yeah.
Yeah, maybe. Wait. You have a question? Great.
So we've got a question via Zoom. So if you'd like to unmute Yevgeny, or I can read it out, whichever comes first. Okay, I'll read it out. So what would happen if you had energy losses at the wave's free interface, aka wave C ice inelastic interactions?
Oh, so this is a person who's working on the problem of the interaction of surface gravity waves and sea ice.
So they're from the National Oceanography Center here.
Yeah. So what would happen is, of course, you get damping. I don't know how strong the damping is, but of course, I've seen pictures and movies where you clearly see that things get smoother and smoother. So I would expect that will kill the instability.
Okay, thank you. And there was just a comment to Joel. Most of the oil rigs damage came from freak waves data from industry. So, okay, that's it from online.
But can I add to that? It's very nice that the evidence came from the oil industry, but I can tell you it was very hard for us to get access to it. So that hindered the development of this field by 20 years.
Thank you.
Okay.
Thank you very much. Thanks. Let's take our